You might assume a computer's math is a slow process of borrowing numbers, but the hardware has a physical shortcut that skips traditional calculation entirely. When writing code, you usually use math humans can easily read, like 5 plus 10, but the computer has to translate every single one of those instructions into binary, long strings of ones and zeros. That translation takes effort. Standard arithmetic acts a lot like building a product piece by piece on an assembly line. It requires the processor to read the high-level math, convert it, calculate it, and store it, all of which uses up memory and cycle time. Bitwise operators are the tools that let us bypass that heavy lifting. Instead of asking the processor to do human math, we can manipulate the raw binary data directly as it moves along the conveyor belt. Standard logical operators look at a broad state, checking if an entire condition is true or false. Bitwise operators are much more granular. They zoom in to compare data switch by switch, bit by bit. Directly manipulating bits helps the hardware reach an answer in fewer steps. This is why these operations are a staple in performance-heavy tasks where every microsecond counts. To manage these bits, the digital factory floor uses 3 main sorting scanners: AND, OR, XOR. These act as filters for the ones and zeros passing through. The AND operator requires both input bits to be 1 to output a 1. The OR operator needs only a single 1 in either input to output a 1. The XOR operator looks for differences, outputting a 1 only when inputs are mismatched. We combine these to create a bitwise mask. It functions exactly like a physical stencil dropped over the conveyor belt. The stencil lets specific bits pass through, allowing you to toggle specific flags without touching any of the surrounding data. Masks give you surgical precision. You could alter tiny pieces of a data stream and know that the surrounding information remains untouched and unbroken. Bitwise logic provides high-speed shortcuts for common math problems that usually require several steps of division or multiplication. To check if a number is odd or even, an AND filter isolates the rightmost digit. 1 means odd, 0 means even. To verify a power of 2, comparing a number against itself minus 1 using an AND operator yields all zeros. The most direct shortcuts on the line are the shift operators, left shift and right shift. Instead of performing slow calculations, these operators physically move the binary data blocks to the left or right directly on the belt. When a row of binary boxes slides 1 space to the left, the total value doubles, physically multiplying by a power of 2. Shifting to the right does the opposite. The final number drops off, and the value is instantly halved, providing hardware-level division. Utilizing these physical movements instead of standard arithmetic is a primary way to optimize software that handles massive amounts of data. When multiple operators appear in a single line of code, the computer follows a strict set of rules, a factory manual, to decide which one to handle first. This is operator precedence. It is a hard-coded priority list. Even in a complex equation, the computer will autonomously target the highest priority operation, like multiplication, before moving on to others. You can override this order using parentheses. By grouping a specific section together, you force the computer to evaluate that part first, regardless of the default priority. If 2 operators have the exact same priority level, the system uses associativity. In these cases, the computer simply reads the line from left to right, processing each part in order. Understanding these rules prevents logic errors. It ensures that no matter how complex your code becomes, the final outcome is always predictable and accurate. The final rule of the factory floor governs who has access to specific tools. This is variable scope, the clearance system that determines where a piece of data can be used. Local scope is like a temporary workspace on the factory floor. When you create a variable inside a specific function, it only exists while that task is being performed. As soon as the task ends, the variable is cleared from memory. Global scope is more like a shared bulletin board in the factory lobby. Any variable placed here is accessible to every function in the file, making it easy to reach but harder to keep secure. Relying too much on global variables can lead to messy, confusing code. This is why we generally prefer strict local scoping. It keeps memory usage low and ensures that data isn't changed by mistake. Mastering these Bitwise shortcuts and organization rules changes the way you look at a program. It helps you move past writing basic instructions and start building code that is as efficient and organized as the hardware it runs on.